Thank you, Hugo. Thank you for the kind introduction. And good morning, everyone. I'm very excited to be here. Thank you for giving me the opportunity to share what my group's been up to over the last sort of 2 years in the adventures of alchemical free energy calculations. So yeah, 2 topics from A to Z, active learning to Zinc. We're going to start out with the Zinc story and then move back to A, because why not? So actually, as I was just sitting down there, I got a push notification from The Guardian saying, oh, we really need to tackle antimicrobial resistance. And in fact, this is kind of my main motivator of why we're looking at metalloproteins, in particular zinc proteins. So, no. Yeah. So bacteria have many different ways of gaining resistances. But so if we have this guy here, typically you have penicillin-binding proteins that help build bacterial cell walls in proteins. And if you give an antibiotic, such as a beta-lactam antibiotic, it will inhibit this, and the bacterium can no longer replicate. So that's great. However, if some bacteria do express beta-lactamases, then that is an issue because the beta-lactamases can hydrolyze the lactam rings in the lactam-like antibiotics, which means the bacterium gains resistances. So one of the ways to tackle this is trying to come up with combination therapeutics, and AstraZeneca has done a great job with avibactam, for example. But one of the challenges is, so how can we actually create things that work against all classes of beta-lactamases, in particular metallo-beta-lactamases? And as such, I thought, well, how good are our current methods for targeting beta-lactamases with alchemical free energy calculations? So how good can we actually predict a binding affinity against beta-lactamases? And this is for serine beta-lactamases, but also metallo-beta-lactamases. So typically, we are interested in computing some kind of delta G. So we have a target, we have a bunch of compounds, and we have a computational method that tells us what is best or worst. Ideally, it gives us a value like a delta G. We ideally compare that to some kind of experiment. They may agree, they may not agree. Ideally, we want them to agree, right? So we have different methods of doing this. We could do something like docking. We can use dynamics-based methods, or we could even use machine learning-based methods. Given that we're at an alchemical free energy calculation event, I'm going to talk about the dynamics-based methods. So again, we have a potential pool of ligands. We would like to understand how they bind to a particular protein target. So if you think of it thermodynamically, we have a ligand and protein binding and unbinding. We can ideally want to compute something like a K-on and a K-off rate. That will be related to our concentrations of our ligand and our receptor, and then the ligand-receptor complex concentration. And from that, we can actually derive a free energy of binding, delta G. That is what we're after. Now, where's the problem? Well, the problem lies in this K-on and K-off and molecular dynamics simulations, right? So here is a very short trajectory of a protein-ligand system. Nothing much moves, right? Even if we look at, I don't know, 500 nanoseconds, not much happens. So if we want to reach sort of typical off rates, this can be very slow, so it can be the slowest seconds. If we want to simulate a K-off or K-on even at 300 to 600 nanoseconds a day for a typical protein-ligand system, not so great. We have to wait millions of years, and thankfully, well, we need to invent better ways of doing that, and the alchemical free energy calculation methods are really there to help us with that problem. So what is alchemy? I think Phil already did this very nicely, so I'll go through it quite quickly, and hopefully most of you are aware of it anyway. But so here the challenge is we have ligand 1 binding to a protein, and that binding and unbinding simulation is really hard, right? But often we're interested in ligands that are similar, so not like in the absolute calculations, but in relative calculations. We have a congeneric series, we have similar compounds. So we want to know what is the difference between ligand 1 binding to the protein and ligand 2 binding to the protein. And again, this is still hard, this difference, but in a computer, we can basically alchemically modify our ligand 1 to ligand 2 by fiddling with the potential energy function effectively. Typically, this is done through a lambda parameter. And then, because free energy is a state function, we can actually write down this beautiful thermodynamic cycle and get this relative free energy difference. So that's great. We've now computed a free energy difference between two compounds. Fantastic. Typically, we want to do that more often, right? We're interested in many different ligands. So how do we get there? Well, here's an example of two ligands. These are two heteroaryl phosphonates from a ligand series that came out of Yu Chen's group in Florida. So these show activities against different types of beta-lactamases. So we can now compute a relative free energy difference and compare it to the experimental values that were given in that paper. But there are much more ligands, so instead we build up an entire network of calculations. So each of these edges is now one of these thermodynamic cycles, and we can compute a free energy difference for each of them, and in this way build up our entire set of computations, which can then compare to our experiments. Okay. So going back to our bacterium, the series of heteroaryl phosphonates, there's experimental data there. And the reason why we picked it is because these ligands basically have experimental values for metallo-beta-lactamases and serine beta-lactamases. And going back to the sort of outset of this, so how good are our sort of current methods for just targeting these beta-lactamases? Typically, we would expect an accuracy of 1 kcal per mole, fairly decent correlation. So let's see if this is true. We use biosim-space for this and pretty standard sort of amber force fields, and we've run it mostly with GAF at the moment. And we're looking at the KPC2 data. So KPC2 is a serine beta-lactamase. It's a serine beta-lactamase because it's got serines in its active site. And here is an sort of zoom in of the ligand 1 crystal structure. Okay, so we've run these calculations. What do we get? We get a pretty nice agreement, kind of what we would expect from a well-behaved alchemical free energy calculation. So on the x-axis, we've got a delta G of experiments, and on our y-axis, we've got a delta G computed. You can see we've got a mean unsigned error of below 1 kcal per mole and a really good correlation. So that's nice. There's some outliers there, but mostly it's all within this 1 kcal per mole band. All right, so that's great. So the force field we've picked seems to work quite well for these compounds. The way we've modeled protonation states, all of that seems to be OK. Right, how about the same set of ligands now for our metallo-beta-lactamase? So this is VIM2. VIM2 has 2 zinc ions in the binding site. And now the question is, how do we model this? Right, so we thought, well, let's go with the most naive approach we could do. Let's use metal center protein parameter builder to get some parameters for our binding site. Here we show it with ligand 16. So the interesting thing is we have coordination with our ligands. So how do we deal with that? So one way of modeling metal coordination sites would be through a bonded model. The problem is if we introduce a bonded model, doing an alchemical free energy calculation will be hard because suddenly we are mutating our protein with the ligand bonded via the zinc. So that makes it difficult, so not ideal. So instead, OK, let's just use restraints, making sure that we can fit our coordination. Well, we can keep our coordination site, but we have the flexibility to do our alchemical free energy calculations as normal. So what do we get? We turned this cutely model 0 because we've not figured a better name out. But we were quite surprised by how good our correlation actually is. So I'm hiding a lot of complexity. We've looked at some of the outliers in terms of what's happening, but we do get a pretty good mean unsigned error of less than 1 kcal per mole and a fairly reasonable correlation here. Since then, we've gone and looked at an improved version of this, but I'm not going to tell you about all of the details for this because that will be Jasmine Guven's poster, so please go and see her poster. Also, if you're interested in more details of Model 0 and Model 1 calculations, that's where all the details are, and she'll be great at answering all of those questions. Okay, so how do we fit in terms of other benchmarking studies? So this is an old benchmarking study with Flair from 2019, when I was still a postdoc, where we showed that all of the standard sort of Schrödinger benchmark systems work quite well in our version of the free energy implementation we're using. Just a reminder, each bar here is one of these correlation plots. If we now plot our metallo-beta-lactamase and beta-lactamase results here, we're well within sort of expected ranges. So one of the things we've done since is actually define best practices in terms of how do we prepare a protein ligand system to use as a benchmark. And when we looked at our KPC2 and VIM2, we tried to follow this as much as possible. And this is just a reminder, if you are struggling to get your system to work, maybe have a look at the best practices paper for constructing and preparing ligand benchmarks, because it will actually tell you what are the things to look out for, how to look at your statistics and things like that. And then, well, there's also the more conventional best practices of how these systems work in general, or rather the more recent version of the best practices in alchemical free energy calculations in general. And this is where I would like to give a shout out for, well, this is in a live comms journal, so it's a living journal, and we would like to update this. This was published in 2020, so we want to do a version 2.0. So if you're interested in getting involved in updating these best practices, please come and find me, have a chat. This is a link to a Google Doc drive where we can collect and brainstorm ideas of what should go into this new version. I've created a Slack channel on the Alchemistry Slack for best practices version 2. So yeah, please get involved. Right, for the remainder of the talk, I want to do a bit of a gear switch now and move to the A part from the A to Z. So this is all about active learning. This is work done by Rohan Garantla, who's in my group, and he basically went off and did an internship with Excensia last summer, so all of the results I'm presenting here comes out of the work while he was at Excensia. So the point is really that, well, if we want to run many of these alchemical free energy calculations, they do become quite costly. So either in terms of getting compute on a high-performance computing cluster, or in terms of cloud computing. So how can we effectively select compounds for screening with alchemical free energy calculations, and what are the best strategies? So say we have, I don't know, again, a ligand pool, and we want to run a subset of this ligand pool with alchemical free energy calculations, and then basically labeling the data. So we now have a bunch of values for our subset of ligands. We can then train a surrogate model, a machine learning model with that subset of the data, and then use that model to label all of the data, and then basically select the next set of ligands we want to run again, and do this in a whole cycle, which then allows us to pick out, hopefully, the best ligands out of our ligand pool. So the idea with this exercise was really, if we have a fixed set of ligands we want to label, say 360 out of 5,000, do we pick out the top performing ligands? Because that's what we want to be able to do, right? We want to be better than random. So we used 2 different machine learning models for training this. It's a Gaussian process, and a chemprop model, which is a neural network-based model. And basically, at each selection point, we retrain the Gaussian process, and in the chemprop model case, so that's a pre-trained model, but we unfreeze a bunch of layers to then train on those and improve the model. Then the next thing you can ask is, okay, how do we actually do the selection? What is the selection strategy? So if I have a Gaussian process model, it'll give me a bunch of numbers out for my free energies for all of the compounds I'm interested in, and usually it will also give me some kind of uncertainty with it. So either I can explore my chemical space by picking highly uncertainly predicted compounds from the model, or I can exploit my chemical space by picking, oh, I want to now accurately label, or accurately, with alchemical free energy calculations, label my high potency compounds that are predicted by this model. And I want to do this all at a fixed cost. So basically, I do this in multiple cycles of 60 compounds and a maximum number of 360 compounds. So we can also play with the batch size of these cycles. So yeah, we want to understand the batch size, and then the last thing we're looking at is how does noise affect the selection, and I'll talk about that in a moment. Okay, so what are the data sets we use? This is all publicly available data. So we have TIC2, which is probably the most famous benchmark data set ever, which was run in a very large study of 9,997 compounds, and we have 500 and 200 top 5 and top 2% compounds. And then we go down all the way to MPRO, which is quite a small data set that comes out of the COVID moonshot data set. Here we have sort of a distribution of all your affinities for the data set, so you can see that there's quite a large distribution. But yeah, and then if we look at a projection into a UMAT format for TIC2, you can see clusters emerging. This should be taken with a pinch of salt because it all depends on how you parameterize your UMAP. But if you squint well, you can see that in the sort of top 2 clusters is where the top 2% compounds are found. So ideally, when we run everything, we want to be able to identify those top 2 clusters effectively. So what are we interested in terms of predictive metrics? We're interested in recall. So can we recall our top 2% and top 5% compounds? And then also we're looking at things like Spearman row, determination coefficient, and so forth. So here's quite a lot to take in. Ignore the orange ones. That is a different type of Gaussian process model. But the main take home is that effectively, if you have large data sets, the different models perform better, which is unsurprising. And all of them do get recall, which is also good. But then there are some subtle differences that the question is it worth it? Because the Gaussian process is much easier to train than the ChemProp model. Then if you look at things like the protocol, so for large data sets, random exploit seems to perform the best, whereas if you have small data sets, you probably want to look at a random explore-exploit strategy. Right, the last thing I want to talk about is noise. So if we run alchemical free energy calculations, they are noisy. You might not always get a perfect mean unsigned error of, I don't know, 0.5 kcal per mole. So what happens if your labels you produce are noisy? Well, we basically artificially added noise to the data, and at 0.5 sigma, our performance drop in terms of Spearman ranking is not massive, and we can still recall pretty much the same top 2% of compounds. So that's quite promising. If we add too much noise, we lose predictiveness, so that's not great. And that gets me to the take-home. So what we found is that Gaussian processes, because they're easier to train and less data hungry, are quite easy to work with. And as predictors as other models, random explore-exploit is better for large data sets, whereas random exploit is better for large data sets, whereas explore-exploit for small data sets gives you a better recall. In general, keep batch sizes to a medium because you want to be able to parallelize your alchemical free energy calculations. So yeah, that's kind of the main take-homes from here. And with this, I would like to summarize kind of what I've been telling you in the last 20 minutes, that well, I don't think I need to convince you that alchemical free energy calculations are good, because that's why you're here. But they're particularly good for beta-lactamases. They're not as good for metallo-beta-lactamases, but pretty surprisingly good. And then active learning strategies are really good at helping you select your ligands for selection strategies for computing your alchemical free energy calculations. And with that, I would like to thank you for your attention, and I would like to acknowledge people who've done the work, which is Jasmine and Rohan, and then people at Excensia, Ben Cossins, Ben Sutari, and Elspeta. I can't pronounce her surname, I'm sorry. And yeah, thank you very much. That's it.
Thank you very much, Tony. Questions? We have one question here. Oops.
Thank you. Very nice talk. Does this work? Do you understand why the explore step is not so effective in the bigger data set? Could it be that maybe because you have already a limited set of clusters, that's the case, and it could be different if you have a completely blank table where you don't know where you want to go?
I think this is exactly why. So because particularly for the TIC2 data set, I think everything, it's quite a narrow data set in some ways. So I think that's exactly why. And yeah, I think it would be interesting to explore it from a sort of design cycle point of view, whether that would actually work as well. Exactly, but that's much harder to convince people to try and do that. But I think it shows that we are at least doing better than random, I think. So I think even in a real world example, that should be true.
I just actually relate to the previous question, your comment. So basically, Bingqing Wei from Genentech, I've seen this type of active learning work published, and I think a common problem is, like you said, large data set, the exploration part seems to be less important. But actually, if you look at in the prospective sense, it's actually your baseline is shifting. The previous series you discovered or trained will be different from after a series of cycles of design testing. So I think a more realistic text would be you separate the data by chemical series, training on early chemical series and predict the later chemical series, or simply using a temporal approach if you look at a published data set if it's available. And so I think this is something I'm just curious that hopefully more people will do this type of approach and see what kind of a search strategy, exploration versus the exploitation balance would be actually optimal for that type of realistic discovery process.
Yeah, I think the main issue is that I don't easily have access to that kind of data, right? So, which makes it hard for me to, or for us to test it. You can test it maybe in-house in a pharmaceutical company, but yeah, with public data, I don't think there's any public data. Or if there is, please someone tell me. Yeah. Yeah, sure, but yeah.
Okay, so I'm pretty sure that Tony will take some more questions during the coffee break, but we'll move on to our next speaker. Thank you very much again, Tony.